Alright, welcome to chapter 9.4 to 9.6. We're going to talk about the law of conservation of momentum, and this is the start of your conservation laws. And before we get into exactly the conservation of momentum, I want to take a second and review exactly what momentum and impulse are from last class. And so we talked about these two things, momentum and impulse, and you learned that impulse is represented by the symbol J, and it's equal to the average force over the change in time. And this is often in very fast interactions, like kicking a soccer ball or hitting a baseball. Fast interactions. And then we also came up with this idea of momentum, which is a combination of mass and velocity. And so the momentum, P, of an object is equal to its mass times its velocity. So mass in kilograms and velocity in meters per second. And then we also kind of explored this idea of, well, momentum and impulse are kind of the same thing. And there's a theorem about that, which is that the impulse is equal to the change in momentum in a system. And we decided that if an impulse force, and I'm going to call it a force in quotes, if an impulse force is applied to something, anything, like a soccer ball coming at a person's head, right? And then our person's head applies an impulse to that soccer ball, well, what it's actually going to do is change the momentum of that soccer ball. And so we can measure impulse as a change in momentum. And there's like 12 different ways we could write that, but we talked about them last class. And you should have this bell in your head ringing that all of this is really just an extension of Newton's second law of motion and Newton's third law of motion. So just as a really quick review, the second law is that force equals mass times acceleration, right? And we can get an impulse force from here. If we know the impulse and the time, then we can get a force. And if we know the mass, then we can find an acceleration. All of that still applies in linear motion. And then this is also kind of a good example of the third law, which is that for every action, there is an equal and opposite reaction. So as the soccer ball is flying at Jimmy's face, once it hits Jimmy's face, well, there's going to be an equal and opposite reaction. And then even, if Jimmy decides to headbutt back a little bit, then there will be an even bigger opposite reaction. Because he's inserting a force into that. And all of this leads us to the idea of the law of conservation of momentum. And all of these conservation laws are pretty much going to be the same. And what they say is that momentum is never created or destroyed. It's only transformed. And so this can also be said that the total momentum of an isolated system is conserved. And this is a couple of really interesting points that I'm going to harp on. One is this idea of total momentum. This isn't something we've explored yet. We've only talked about the momentum of one object. And the total of that is, well, just the momentum of that object. But when we bring in two objects, especially if they are hurtling towards each other and they're headed for a collision, well, then we've got to consider the total momentum of that system. And then the other interesting part of this is isolated system. And an isolated system is one where no external forces are present. So there's no external, external, and I'm actually going to say net force. And so when we consider a system, it can't be, for instance, it can't be something where there's these extra pushes going on outside of that. If we're going to go look at the collision of two things, then we need to only consider the collision of those two things. The other thing that I want to kind of bring into play here is this idea of total momentum. And so we learned last class that momentum is equal to mass times velocity, but we know from like the second week of school that velocity can have a positive or a negative value. If velocity has a positive value, then we're talking about to the right or upward motion. And if velocity has a negative value, then we're talking about to the left or down. Right? And maybe I should just go ahead and change that to a right arrow. There we go. And so momentum, likewise, can carry a sign, which is why we put the little vector symbol above it. If something has a negative momentum, then the same thing applies. It is moving to the left or down. And if something has a positive momentum, it's moving to the right or up. And so let's say that we have these two objects, and one has a momentum of 5 kilogram meter per second, and the other has a momentum of, I don't know, let's say negative 10 kilogram meter per second. Meter per second. And so then if these two objects are kind of heading towards one another, I know that object 2 is moving to the left because it's got that negative momentum, and I know that object 1 is moving to the right. And if I want to know the total momentum for this system, then since these are vector quantities, I can actually just add them together to get a sum. And so all I have to do is the sum of the momentums is equal to, in this case, 5 plus negative 10, which is really just 5 minus 10, which is negative 5 kilogram meter per second. And that would be the total momentum of that system. And so same equation, right? We're just making sure we now have the correct sign, positive or negative with momentum, and you can add them to get the total momentum of a system. Alright, so let's take that law of conservation of momentum and let's talk about two objects interacting, like a sumo wrestler and a normal human being. Let's say that these two objects, or people in this case, are going to start running at one another in order to win a sumo wrestling match. And you already know who's going to win, right? The more massive person, because they have more inertia. And because they have more inertia and more mass, then they're going to have more force as well. But let's analyze this in terms of conservation of momentum. So we'll look at the initial momentum of both objects to learn a little bit more about how this situation is going to end up. So let's say we have our sumo wrestler who has a mass of 300 kilograms and is moving at 5 meters per second. And so I know that momentum is mass times velocity. And so the initial momentum of my sumo wrestler is going to be 600 kilogram meter per second. And that's a heck of a lot of momentum. And then when I come over to my normal person, this guy's initial momentum is his mass times velocity, which is going to be 50 kilograms times 2 meters per second, which will give him an initial velocity of 100 kilogram meters per second. And I know that that is a negative 2 meters per second, and so his initial momentum needs to actually be negative 100 kilogram meters per second. And so when I talk about the initial momentum of the system total, right, the sum of the momentums, I'm looking at 600 plus negative 100, which is going to give me a total momentum of 500 kilogram meters per second, right, for the initial momentum of the system. Because of the law of conservation of momentum, I know that the initial momentum is going to be equal to the final momentum of the system. So let's say these two guys run into each other and they bounce off one another. I know that the initial total momentum of the system is 500 kilogram meters per second, and so that's got to be the final momentum. I know that. Let's say I measure the small guy to be moving after this collision to the right at 4 meters per second, and let's say that I want to know the final velocity of our sumo wrestler. Okay? And so then I know that the final momentum is 500. And so I'll go ahead and do 500 equals. My little guy is moving to the right, so he's going to be the positive one, and it's going to be mv of this guy to the right plus mv, right, or the momentum of the sumo wrestler. I know my guy to the right is going to be 50 times 4. His mass is still 50. He didn't lose any weight. And so his momentum is going to be 200 kilogram meters per second to the right. Mass of my sumo wrestler didn't change. It's still 300 kilograms, but I want to know the velocity of that sumo wrestler, and I don't know it just yet. So I've got to solve for v. What I'll do is I'll subtract 200 from both sides to get rid of that first, and I'm left with 300 over here equals 300 v. I'm going to divide by 300, and what I will get is that 1, my sumo wrestler is going to be moving at 1 meter per second to the left after this collision. And then I asked myself, okay, well, does that make sense that the more massive object would be moving slower after this collision? Oh, yes, it does. And it's going to be moving much slower than the little tiny guy. Because he has less mass, it's easy to move. Right, so when we have two objects, because of this law of conservation of momentum, we're going to say that the total initial momentum is equal to the total final momentum. And so if we have two objects, then it's going to be the mass of object 1 and its initial velocity plus the mass of object 2 and its initial velocity. Masses usually stay the same after collisions. We're not creating and destroying mass here. But afterwards they will each both have a final velocity, and we can set our formulas up like this. If we have 3 objects interacting, then we have 3 objects interacting. But initial momentum is always going to be equal to final momentum in these problems. Alright, so let's think about maybe a guy on a skateboard. This is kind of like an impulse or a quick interaction, a combining or interaction of objects with masses and velocities. Let's say I have a guy who starts running at a skateboard, and the data is off to the right, and then the guy hops on the skateboard, and I want to know how fast both of them are going after that interaction has occurred. So our guy is 70 kilograms, and he's going to be running at 2 meters per second to the right. And so I'll just go ahead and label that. This is going to be meters per second, and he's 70 kilograms. The board is 2 kilograms, and in this initial kind of starting state, its velocity is 0. It's just sitting there. And then I want to know what's the final velocity of this system. And so I'm going to start off with this as a conservation of momentum problem. I know that the total initial momentum is going to equal the total final momentum. And so let's go ahead and figure out that initial situation. Our guy is 70 kilograms, so it'll be mv of the guy plus mv of the board. The guy is 70 kilograms. He's moving at 2 meters per second. That gives him a momentum of 140 plus, and then the mass of the board is 2 kilograms, but it's not moving, and so there is no momentum on that board. And so my initial momentum has to be 140 kilogram meters per second, right? And I know this is going to be the same as my final momentum. I just carried that down. I didn't do anything to it. And I want to know how fast they're going at the end. And so at the end, I can kind of think of these as one object, both man and board. And so the momentum final is 140. And I know it's going to be equal to the mass times the velocity of the ending object. The ending object is actually the mass of the guy and the board. And so I'm going to put in 72 kilograms for my mass. And I'm going to have to solve for my velocity. And in order to do that, I need to divide both sides by 72. And divide both sides by 72. Right? They cancel here. And the final velocity of my guy and the board is going to be 1.94 meters per second. And it's going to be moving to the right still because he's jumping on that board. Yeah, and so it's going to be 1.94 meters per second to the right. And if you think about this, well, yes, it does make sense. If you've ever jumped on a skateboard, you can be running, and then as soon as you jump on it, you actually go a little bit slower than whatever you are running. Be careful. Don't try this at home. Don't run too fast. Skateboards tend to fall out from under you. We can also use initial momentum equals final momentum to find interactions between objects that are initially not moving. So a great example of this is gun recoil. Again, I've got information and data for this system. If I know that a gun shoots a bullet at 300 meters per second, which is pretty close to a good guess for a bullet, what is the recoil velocity of that gun? And so guns tend to give a little bit of a kickback when you shoot them, especially depending on the kind of bullet you're shooting and the kind of gun that you're shooting. And so let's pretend that we have a 3 kilogram gun, a 10 gram bullet, which is 0.01 kilograms, and that bullet fires at 300 meters per second. So what's the recoil velocity of the gun? I'm always going to start this problem with initial momentum equals final momentum of the system. And the momentum here, so I'll do the mass of the gun times the initial velocity of the gun. Before it's fired, the gun's not moving, right? And neither is the bullet. And so the total initial velocity of that system is going to be 0, which means that the total final momentum has to be equal to 0 as well. And so I can take this and I can say, okay, well, 0 kilogram meters per second is equal to, let's imagine that this bullet is going to go to the right. And so we'll say the M of the bullet and the V of the bullet, plus the mass of the gun and the velocity of the gun in that final situation. Well, I know the mass of the bullet, right? It's 0.01 kilograms, and it's going to be going 300 meters per second to the right, plus, and then I know the mass of the gun is 3 kilograms, but what I want to know is the final recoil velocity of the gun. And so I need to go ahead and simplify this first step. 0.01 times 300, which is going to be 3, plus, I'll just bring down the things I didn't do anything to. 0 is still over here. And so then to solve, I need to subtract 3 from both sides. Minus 3 equals 3 VG, and then I would divide both sides by 3, and what I find is that the final velocity of that gun is going to be -1 meters per second, and that does make sense, and it's a very short thing, but if the bullet is firing to the right, then the gun is going to recoil to the left, which accounts for the symbol of that velocity. Again, you've got these quick interactions, and we can use the law of conservation of momentum to analyze those. Alright, and so what I want to do at this point is take a second and talk about collisions. Up to this point, or interactions maybe is a better word for them. Up to this point, we've talked about two objects coming together, and then once they collide, they rebound or bounce off one another. However, this is not always the case in life. Sometimes things come hurtling at each other, and then depending on the masses of those objects and kind of the materials that they're made of, those two things can stick together and then move as one. We see car wrecks that happen like this a lot, especially between larger vehicles and smaller vehicles. So we're going to introduce these two vocabulary words, perfectly elastic and perfectly inelastic. Perfectly elastic says that in a collision, none of the energy of the momentum is lost as heat. And if you take your hands and kind of rub them together, or if you've ever very quickly, run into something or had an interaction with something where you could feel the heat, you know that some of that energy is lost as heat. Well, okay, so perfectly elastic, we imagine that all of that energy is perfectly conserved, and these objects bounce, right? And they bounce off of one another. A perfectly inelastic collision, however, is when these objects stick. And this is going to be important in the afterward scenario, and how you treat the masses. In the afterward scenario for a perfectly elastic collision, the masses are still separate. There's still two objects, and they're going to be going different ways, and so you need to treat them as separate. For a perfectly inelastic collision where two things collide and they stick together, you can imagine the masses of those objects combining, right? So let's say that I have, like the guy on the skateboard. I, in that initial situation, had a guy and a skateboard, and in the after situation, I had guy and skateboard, right? And so when you're reading a situation, sometimes it'll be really explicit about it being perfectly elastic or perfectly inelastic and then bouncing or sticking. But do read carefully and do be careful about that when you're analyzing initial and final momentums. The last part that I'm going to talk about is chapter 9.6 on page 275, which is momentum in two dimensions. And so up to this point, we've talked about two masses, M1 and M2, kind of colliding and only in one dimension. And the truth is that the real world doesn't act like this. The real world, things act in two dimensions, and so we need to be able to analyze that accordingly. So to talk about this, what I'm going to do is pretend that I've set up this coordinate plane, right, with an x, and a y-axis. And let's say within this coordinate plane, I have, a building, right, and some mischievous person who is going to throw water balloons off of this building at people passing by on the street, right? These water balloons have masses and they'll have velocities, but they're not acting perfectly in the x direction or perfectly in the y direction. Let's say that each water balloon has a mass of 5 kilograms. They're big water balloons. And this person is hurling them with an initial velocity of 10 meters per second. And so this will be 10 meters per second. And they're hurtling them at an angle theta of, 20 degrees down, right? Just like we talked about velocities in the x and y direction, or having x and y components, and accelerations having x and y components, well, momentum is a vector, and guess what? It can have x and y components, and we need to be able to separate those things out. Alright, at this point you should have guessed what we're going to have to do. Welcome back, trigonometry. We're so excited to have you again. And we are going to use trig to find out the x component and the y component of this momentum using trig. And so if this person is at 20 degrees, right, and let's say we'll find the momentum along the x first, and then we'll find the momentum along the y. the component of the momentum along the x is going to be opposite over hypotenuse. So that'll be, we know that sine of theta equals opposite over hypotenuse. In this case, we're working with an angle of 20 degrees. And we don't know the opposite side, but we do know that the hypotenuse is 10. And so what we're going to try and find, maybe I should make that not look so much like theta. What we're going to try and find is the opposite, so I need to multiply both sides by 10. Multiply both sides by 10. And 10 times, alright, and I'm sorry, 10 times sine of 20 degrees is going to be 3.42. And so the x component of this momentum is going to be 3.42 kilogram meters per second. And so we'll go ahead and label that 3.42. And if you wanted to, at this point, you could go ahead and use the Pythagorean theorem that 10 squared equals 3.42 squared plus the momentum along the y squared. And you could solve for momentum along the y without trig once you get one of the x and y components. The tricky part to all of this that you guys are not going to like, but I won't hammer it home, I promise I won't kill you on trig, I know you know how to do it, is that in these kinds of systems, when momentum is conserved, right, when the initial momentum equals the final momentum, this is in both the x and the y direction. So for the x direction, or for the x component of things, the initial x component of the momentum equals the initial x component of the final momentum, and the initial y component of the momentum is equal to the final y component of the momentum. Right, and here is your homework for 9.4 through 9.6. We are not going to do 9.7, dealing with angular momentum. Pretty much the same, just has to do with rotational motion. I prefer that you know these very well. And so when you show up in class tomorrow at 10:45, have these homework problems written down. And so here's the trick to flipping the classroom. Have these homework problems written down, and I will know that you have watched this video. And if you do not have these problems written down, then I will know that you have not watched this video. Alright, so pause the video, write the problems down, and I will see you tomorrow in class. Happy studying. Thanks for listening. Have a great night.